Okay, welcome to the Advanced Solid State Physics 2. Today, I will give you an outline of what this course is about. And for those of you who have not taken Advanced Solid State 1 that I gave in the previous years or previous semesters, please raise your hand. So this course is about using second quantization technique to actually perform some calculations in solid state physics, especially to learn how to use Green's function methods and perturbation theory in quantum many-body system. So the primary goal is to learn Green's function methods. The Green's function is a very important quantity that all of the solid state physicists should learn. Regardless whether you are a theorist or experimentalist, you all need that because you need to know what you measured if you are experimentalist. And those quantities that you measure in the lab are usually functions of correlation function, 关联函数, 格林函数. But if you are serious, of course, you should know how to calculate these things because these things can be measured in the lab. So for the same reason, because our interests in the lab or this quantum many-body phenomena could be formulated in some or another in terms of the Green's function. You need to know the Green's function. And how to perform such a Green's function calculation is the goal of this course. And to use this Green's function method, you first need to know the creation-destruction operator in advanced solid state 1. Because that's the reason why I asked you whether you learned that. Apparently, all of you have learned that. That's good. So I will not repeat this introduction part of the creation-destruction operator and assume that everyone learned that already. And I will give you some outlines which already in this syllabus that you can check on the website. But I should also write them down in the blackboard. And also some reference books, textbooks that are useful in this course, and also the grading policy and so on and so forth. So there's no real content that will be introduced today, but you will see what you will learn in the semester. Okay, so you already know my name, but it's worthwhile spending a little time repeating this basic information. Great. So about these textbooks, I already brought them here. So the main textbook is this one, Many-Body Quantum Theory in Condensed Matter Physics, an introduction written by Browse and Flansburg. And this is also the textbook that I used to teach Advanced Solid State 1. And you could read from the very beginning the review of the introduction level of solid state physics and also the second quantization, formalism, and then Green's function and so on and so forth. Okay, so this is an excellent graduate level textbooks on quantum many-body theory. And the other useful references are the following. This one, Quantum Theory of Many Particle Systems by Vetter and Velochka. It's really time-consuming to write down all these names of the books. Okay, and there's a very thick textbook for many well-known physics department in US and Europe, which is this one by Gerard Mann, Many Particle Systems. And there's a very advanced references, which is called Quantum Many Particle Systems by two theorists called Neglett and Oland. And there are other two books, or one. Let me just write it here. Green's Functions for Solid State Physicists by Doniak and Sonheimer. You can also find this list of textbooks in this course web page. Most of the lectures for this course follow Flansburg, and some of them follow Vetter or Mann, and very little of lecture notes come from Neglett or Land, but the last one is a very useful reference for solid state theorists and also experimentalists. And this book, Green's Function for Solid State Physics, is precisely the target of this course, that it covers all physical observables that you could measure in the experiments that are Green's functions, and instruct you how to calculate this Green's function. But this is a very concise book and very short. So There are no great details in that book, but this book gives you a very good sense of what you should learn about Green's function and what can you do about Green's function, what is useful about Green's functions. So you don't have to buy all these textbooks unless you want to, but you could always borrow this Flansburgh from the library or from any of the students around here or in, say, neighboring universities or whatever. And I think these references are found in the library always. It's good to have one, but you don't need to buy them. So let's come to this outline. As I mentioned, this is the course mainly about Green's function technique. And of course, I should give you a very brief introduction to Green's functions. Concept of Green's function go back to the classical mechanics, but even single particle quantum mechanics, you could learn this Green's function. It's nothing but the correlation function, the probability amplitude that an electron is destroyed at time 0 and created in some finite time t, and you evaluate this kind of expression value of the pair of operator psi dagger t, psi 0, which tells you how this single quantum particle time evolved from t equals 0 to t equals t. What is the probability amplitude that you can find a quantum particle at time equals t, but this particle was there at time equals 0. So of course you could imagine you could also calculate the special correlations of a single quantum particle that imagine that this particle stay here at x equals 0 and then it moves to a different location, space-time location. So what is the probability that the single quantum particle evolves from this time and space coordinate to that time, space and time coordinate? Okay, so it is the time and space correlation of a single quantum particle from one spatial and time coordinate to another one. So this is called transition amplitude in quantum mechanics, or the probability amplitude of a single quantum particle to go from one space and time coordinate to another one. So you know this very well from single particle quantum mechanics, but here we will learn how to calculate these things in the background of many quantum particle systems, so-called the quantum many-body system. So this is a highly non-trivial problem if you want to calculate this transition amplitude of a single electron in the background of many electron ion system. This is way too complicated than you can imagine. But for a single quantum particle, it's not so hard to compute this thing. So this is the heart of our course, that we like to calculate this thing. That's it. But it is easier said than done. So you have learned as time goes by that this quantity is really difficult to capture if you are dealing with millions or millions of electrons and ions. But we have a way to approach this quantity approximately, namely the perturbation theory. So that's the first thing, which is the introduction to Green's function, the concept and applications. So as I mentioned, almost all quantities that you can measure in the lab can be formulated in some way or another, some sort of a correlation function. It's not just a single particle creation destruction operator product, but you could imagine that this is the spin-spin correlation function, or density-density correlation function, the current-current correlation functions, and so on and so forth. And we will introduce all sorts of correlation functions, or Green's functions, and their applications in the real physical system or measurable quantities. So after that, we will start from the very beginning, which is the free particle, and we can define Green's function for free particles. So that's trivial, but it's not so trivial. As I mentioned in your single particle quantum mechanics, you may have found this quantity, but I believe that you have not studied or learned the Fourier transformations of that Green's function in momentum and frequency space. So if I denote this G as this kind of a single particle correlation function, and we will learn how to Fourier transform this correlation function gxt to its Fourier space, which is momentum and frequency space by a Fourier transformation. And this is a very important quantity that has direct relevance for physical observables in the lab. But we will start from the simplest possible system, which is the free electron systems. And even the free particle is not so trivial to really perform such a Fourier transformations. And of course, we should state as simple as possible from the beginning that we stick to the zero temperature limit. So it's the simplest possible scenario that you can imagine, the zero temperature free particle Green's functions. Of course, we know that all these realistic solid-state materials live at finite temperatures, right? So for a finite temperature Green's function, it is really technically involved. So, but we should define this finite temperature Green's function. And this involves computation of a partition function. Imagine that you take the expression value of such a single particle Green's function, not at zero temperature, but at finite temperature. Then following the standard statistical mechanics, you know that you need to calculate this partition function first, right? But how do you calculate this partition function and also embed it into this kind of expression value of a product of the two quantum single particle operators? So this is a highly non-trivial task. So it involves some mathematical and physics manipulations of this quantity. But this is the most relevant quantity for the experiments, because we know very well that everything that you measured in the lab is done at finite temperatures. There's no absolute zero temperature measurement because you cannot reach the zero temperature limit in any case. But you could actually assume that when temperature is really low, that your results are approximately zero temperature results. Nevertheless, people, both serious and experimentalists, are interested in low temperature properties of many-body phenomena, and so you should not always stick to zero temperature because this is not useful. You need to know the temperature dependence of a quantity. But once you want to know the temperature dependence of your quantity, then the difficulty arises because you have no way to calculate this thing if you do not learn this technique. This is way too difficult. So we need to play some mathematical tricks, which requires a lot of time and effort in these lectures to learn how to really incorporate this partition function in this Green's function calculation, and it involves this Feynman's path integral approach that you already learned in quantum mechanics. So then we will introduce this very important systematic approach, which is called linear response theory, and this Mossel-Borel frequency formulation. So when we write down this Green's function, and we could analyze this kind of physical response to the small external field, like a small electric field or a small magnetic field, and we could actually perturb the system around by introducing a small electric or magnetic field, and then we should learn how to take the linear response in the linear order in a small field, and that linear response tells you the quantities that is linearly proportional to your external field, and that is precisely what you measure in the lab. And that linear response quantity is related to this Green's function precisely. And this is a more mathematical definition of your Green's function, that you imagine that you want to measure this spin or magnetic susceptibility of your magnetic material. What you want to do is you want to apply an external small magnetic field, and you measure this response to this small field by measuring this magnetization of your system, because you apply the small magnetic field, and for magnetic materials you should get some response. And then you could take this small response of your magnetization relative to the zero field magnetization, and you divide it by your small magnetic field, and this is precisely your spin susceptibility, 磁化率. So the magnetic or spin susceptibility is formally defined by the ratio of the magnetization, that is to the linear order in the field, and divided by this field. And this susceptibility then, following this definition, is independent of the field, because the M is linearly in B, and you actually divide this B downstairs in the denominator, so this field dependence is gone. So as a result, you can measure this so-called spin susceptibility of your magnetic material, and this spin susceptibility is nothing but the spin-spin correlation function. Okay, so we will formally introduce this, which is state that you measure the correlation between the two spin operators. First one is that 0, 0 times 0 spatial coordinate 0, and another is the time t and x equals non-zero location. So you want to know how the spin operator involved in space and time coordinates, and this quantity is precisely this definition of the spin susceptibility that you measure in the lab. Okay, so we should make such identifications later on, but here I just illustrate this as an example that when you measure this small response to linear order in your external field, what you measure is nothing but the correlation function. And this is the thing that we want to learn how to calculate, and this is the thing that you take the measurement in the lab. So there's a one-to-one correspondence between the theoretical formulation of the spin-spin correlation function and experimentally measurable quantities such as magnetic susceptibility. So this really powerful method which allows you to relate the theoretical quantity and experimental measurable quantities. Okay, so everything you calculate could be checked experimentally, and everything that you measured could be calculated in the theory. So it's a two-way street, and in this course you will learn two things. One is to calculate these quantities, another is what is corresponding observables that you can measure in the lab. So you could consider this course as one stone that you could shoot down two birds. All right? So this is the beauty of this course, that you simultaneously learned theoretical and experimental physics. Great. And Matsubara frequency formulation is nothing but the Fourier transformation of the Green's function from the real time to the frequency domain, and you learn how to define this Matsubara frequency for different particles. For example, the fermions and bosons have different values of the Matsubara frequencies, and we will talk about this Matsubara domain later. In other words, at finite temperatures, the Green's function calculations involve a discrete time Fourier transformations from real time to this Matsubara frequency domain, and fermionic and bosonic particles have different symmetries, values of this discrete Matsubara frequencies, and this will be discussed in our course later. Okay? Any questions? Sounds easy, but it's not easy at all. But precisely because this is not an easy course, and I'm proud to say that in Taiwan there's no other course like this. You are lucky guys that you learn these techniques here. And if you look at all the websites in all other universities in Taiwan, there's no course like this given in Taiwan. But this is really the hardcore training for a condensed matter theorist or experimentalist, and I've given such courses more than 15 years. But still, this is a very few courses that could be offered in Taiwan. So let's take a very brief break, and I will continue introducing the remaining of the outline of the course. Oh, okay. Yeah, this is, I forgot to mention this. This textbook or reference book is useful when you study magnetic properties of solids, such as ferromagnetic or antiferromagnetic materials. And there you will find some mean field approach which allows you to calculate this correlation function of the precise spin susceptibility or magnetization of your system. So it's not required. We may or may not have time to discuss this, but some content in this book has already been mentioned in my previous course on advanced solid state 1. For example, this Hostin-Permakov approach or spin wave analysis and so on. But you could continue to calculate this Green's function or spin-spin correlation functions from the mean field solutions of this in that book. So it's useful when you study magnetic materials. But this becomes more useful only when you are familiar with the Green's function technique. So it's a more advanced references. So the really fundamental and steps that you learn this is this book. So this is of course there are other similar books such as quantum antibody theory in condensed matter written by Piers Coleman and so on. But I find that this book is really friendly to the graduate students because it comes from single particle quantum mechanics that everyone is familiar with. So there's no jump around. So it started from the zero and scratch, and you start to build up your knowledge about this creation destruction operator, and also the physics that you already learned from introduction level to solid state. So it's always come back to physics. So if you could solve all these homework problems in all chapters, which you can find in the very end of the book, then you don't need to come to the course anymore. But it's really a difficult task, especially in the later chapters where you apply this Green's function approach to calculate many sophisticated systems such as the superconducting states and also disordered system, many particle disorder system. So these becomes really technical part, and so you should learn step by step from the scratch. So after this introduction to this Green's function at zero and finite temperature, we start to introduce perturbation theory. So you know very well from your single particle quantum mechanics that you could perturb your system around the unperturbed eigenstate of the Hamiltonian and order by order in this small weak interaction strengths. But this is single particle quantum mechanics. So in many body system, you have countless electrons and ions surrounding the single particle, single electron. So how can you perturb the system around? So you need to know how to perform such a perturbation in a many-body environment. So it's called the many-particle perturbation theory, which is highly non-trivial. And we will introduce this by this Feynman's rules, so-called Feynman diagrams, and also weak theory. So the Feynman diagram or Feynman rules are first introduced in the context of high-energy physics. So if you learn this quantum field theory in the context of high-energy or particle physics, and you will learn how to draw these diagrams, these fancy diagrams like this, like diagrams in the cover, like the diagrams in this cover. So the diagrams are your nightmare, so your dream will be full of these diagrams. But this is a necessary techniques that you need to learn in order to really correctly calculate this correlation function in a perturbed manner. So imagine that I introduce the external potential, which is very weak, and then we start to perturb it around, and you know this unperturbed exact eigenstate of the many-particle system, but the problem is how to do the perturbation in this many-body environment. And Feynman is a genius theorist who invented this diagrammatic technique, which allows us to systematically study order by order in this interaction strengths to estimate these correlation functions in terms of a small perturbation, and then we could evaluate this thing and find a temperature perturbatively. So of course, in this complicated many-body problem, one cannot solve this problem exactly, or we cannot calculate this thing exactly. So we need to rely on some approximation, and perturbative expansion is a useful and standard way to capture these correlation functions order by order, but the problem is there are many particles. Okay, so how do you systematically evaluate these things order by order in a systematic way? So this is the hard problem, but fortunately Feynman already solved this problem for us, and we just need to follow his plans and proposals and get used to those diagrammatic representation of these things in the perturbed expansion. So that's what we will learn. And then later we'll take some recontractions to contract all these messy perturbed expansions, and then later we could re-express this expansions in terms of so-called Beer-Green's functions. So the Beer-Green's functions refers to the fact that you don't consider any interactions in your system. It's the non-interacting many-body Green's function that we already learned how to calculate, but eventually these interacting correlation functions could be reduced to summation of many different non-interacting Green's functions. It's a combination of various non-interacting Green's functions. So time is up for today, and we will continue introducing this outline in our next lecture. Thank you for coming.